Today I'm actually going to go and work a problem out that confused me a lot on my last test, and I'm just here to try to explain this in a way that makes sense to other people. So the problem that I had with problem number 4 was with problem number 4. So okay, the problem statement reads: you put a thin metal pot containing 2 kilograms room temperature, blah 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 blah, a bunch of numbers, right? And we want to find the change E thermal of the water. So okay, so you might get confused, you might be a little scared at first, but if you think about it, and we learned throughout the course, we actually have a specific formula for delta E thermal, right? So delta E therm is going to be equal to MC delta T, right? MC, that's a capital C, by the way, delta T, which basically means that the change in thermal energy is going to be equal to the mass times the heat capacity of the specific object times the amount of time that we're considering, right? So we know all of these variables are here. So if we know all those variables, we can actually plug it in and find E thermal, straight away. So let's go ahead and do that. So we know we have the thin metal pot, which is, we want to convert it to grams because it's heat capacities in grams per degree Celsius. So we want to convert that to grams. So we know it's 2,000 grams, right? 2,000 grams times the specific heat capacity of water, which is 4.2 joules per gram per degree Celsius, right? Degrees Celsius, and then we want to multiply that by our change in temperature, which is 100 degrees Celsius minus 12 degrees Celsius. So this problem actually breaks down. It's pretty simple, really easy, really nice, and you get delta E thermal is equal to 707, some really big number, 739,200 joules, right? That's our answer. That's our answer. Okay, so we also want the next question, the next part asks us to find the thermal energy transfer energy Q into the water from the surroundings. What I've learned with energy problems is you always want to go back to our very first fundamental principle, as Dr. Schatz has always been drilling into our head all semester, is delta E is equal to Q plus W. Right? That's our big equation that we always go back to. So we can say that delta E therm is going to be equal to work plus Q. Delta E equals work. Oh, sorry, that's not right. Delta E therm, because we have no other kinetic energies and whatnot, it's just thermal energy, is equal to Q plus W. And delta E is equal to our delta therm, of course, because there's no other kinetic, there's no other energies. So the thermal energy is the only energy that we're concerned with for right now. So if you want to find Q, we just have to rearrange this equation, and you want to go back and say, Q is equal to negative delta E therm minus the work done on the system. Plus the work done on the system, right? So it ends up being this problem. It gave me a lot of trouble because I was panicking and I wasn't sure how to approach this problem. We hadn't done this type of we did do this type of problem, but I was as I was panicking, I was scared, and I didn't go back to the fundamental principles as always. And if you did, this problem would actually break down really easily. So we know the work done on the system. It's the beater thing that's happening for an extended amount of time, and we know delta E therm, which we just calculated. Right. So the work done on the system is going to be force times delta T. And you did it for what, 15 minutes? As the problem statement says. Yeah. So we beat the water for 15 minutes. So that 15 times 60 is whatever many seconds. And so we can actually write out this equation quite easily. So it's quite Q, which we're trying to find, is negative delta E therm, which is 739,200 joules, right? Minus, which was our work, 100 joules per second, which is our force per second, right? Times 15 minutes times the conversion factor, which is 60 seconds over 1 minute per minute. Right? And so you simplify all that down and you get 649,200 Oh, that's bad. I didn't write that out right. 649,200 0.9200 joules. Really nice, really simple. This next question is where our fundamental principle. You just got to think about your fundamental principle more than anything else. I got a lot of trouble into here because I thought I had our chemistry background, and I said, the work done Q, it has to go in and out of the system or whatnot, and then so it has to be equal to what we just found. When really it's not. It's along this. It's kind of like the same thinking, but not quite. So let's go back to our fundamental system, fundamental principle, and we say that the energy conservation of energy is what this is what gets getting at, right? So we have delta E of our system plus delta E of the surroundings has to equal 0. Has to equal 0, right? That's just our fundamental principle. So if we we break this down, we say a delta E of our system is actually equal to our delta E thermal. I don't know why PowerPoint keeps on correcting that, but anyway, is equal to delta E thermal, right? And delta E of our surroundings is actually equal to negative delta E of our system. Because what goes into our system has to come from the surroundings, right? If we take energy from the surroundings, it has to end up in our system. Sorry. So that should be negative E of our system equals delta E of surrounding. So if we know this, it's delta E surroundings. Delta E surroundings is actually the negative of what we found it for our delta E of our system, which is equal to delta E of our therm, well, which we found in part A. So it's basically what I'm trying to get at is it's negative of our part A. And I completely thought when I was doing this that it was the Q that we just found, because I thought it came from the surroundings, so it has to go into the system, and so that's where our change in surroundings is. But it's actually E the system, not Q, not the work or the energy transfer. It's along the same lines, but not quite. Not quite. Alright, so this is our answer at the very end. So let's go to our very last section of our problem. And it has to do with dumping a bunch of potatoes into a pot, right? And finding where it all goes. So go back to our fundamental principle, right? Delta E equals Q plus W. Energy problems are actually really sweet. Alright. And so we can ignore the delta E therm of the pot. And so they basically, when you dump these potatoes and whatnot, let them come to equilibrium, you know that the temperatures are all going to be both of them are going to be the same. So basically both of the delta E thermals are going to be the same. So delta E thermal of the potatoes, right? Potatoes is going to have to equal to delta E of our our pot, right? Because they both come to equilibrium, so we know that they're equal to each other after some time, right? And we can ignore delta E of the pot. So basically, what that says is delta E equals 0. So basically, what I did here is you had delta E therm, or delta E just equal to Q plus W. But because of the little statement that we had up there, Q plus W actually equals 0. And so delta E is actually delta E therm. And then you break it down into the components of the pot, right? And the potatoes. Well, the pot and potatoes actually have the same first 3 letters, so that's kind of dumb of me. But you break the delta E therm into its 2 components, and you know that the right hand side is equal to 0, so you move it over to the other side, right? So we know delta E therm and delta E of the pot to be MC delta T for both sides. So MC delta T, or MCAT, is equal to MC delta T of the other object, right? And from here, it's just plug and chug. And let me just write out the big step, and then go ahead and just fill in the answer, and then go ahead and tell you the answer, because it's not that bad. So we have the mass of our sweet potatoes, right, times the specific heat of the sweet potatoes, plus the mass of the water, plus the heat capacity of the water, right? Well, this should be times. Sorry, this is kind of messy, right? Times the final temperature, is equal to same thing, plus mass of the water, heat capacity of the water times 100 degrees, right? Which is the initial temperatures of the water. The initial temperatures of the water. Basically, I just split the delta T's into initial minus final and go ahead and wrote out this statement. If you solve for this T final, because we know that MC delta T is just T final minus T initial, right? And I just took this initial component and just broke it down for both the potatoes and the water, and I went ahead and did that for you. I wasn't gonna have to like derive it for you. I'm sure you can do it yourself. So if you solve for it, temperature final, what we're looking for, which is 65.7 degrees Celsius. So that's how you solve this problem overall. It makes a lot of sense. Looking back in retrospect, it's really easy because you just go back to what you know, and what you know is the equations, and what you know of the equations comes from your energy principle. And if that's the big takeaway from this problem, I would definitely say go back to your fundamental principle every time, even if you get stuck and even if you get scared, because obviously you're going to get scared and you're going to get if you don't know the equations. So just know the energy principle inside out, and you'll be fine with this problem.